Millman's theorem, which was named after Jacob Millman, is a circuit analysis theorem that applies to a very specific instance when you have a set of voltage sources in parallel with each other. And Millman's theorem allows you in basically one step to convert from that set of parallel voltage sources into a single equivalent voltage source with its associated equivalent resistance. The proof behind it, or the derivation of it, is fairly simple. You just need to use Ohm's law and Kirchhoff's laws, and then the equivalency between voltage source and current source circuits. So basically, to start off with, what we can do is convert this circuit into the form that has current sources. And just to point out what's going on here, we've got voltage source 1, voltage source 2. We have some number of voltage sources that's represented by the dot, 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 and we're out to voltage source n. So this is basically saying that any number of voltage sources can use Millman's theorem. And really the first step in deriving it is to convert this circuit into a set of parallel current sources. So V1 will turn into I1 with R1. V2 will turn into I2 with the parallel R2. And then we'll have some number of sources in between source 2 and the last source there, which becomes current source N with the associated output resistance. And then all of this, of course, is connected to our load. Now I1, of course, is V1 over R1. I2 is V2 over R2. And IN is Vn over Rn. And the R1, R2, and Rn are the same as what's in the initial circuit. Now the combination of these current sources together is fairly simple. Very easy to combine those together to become some equivalent current source. Call it I equivalent, IEQ. And same thing with the R1, R2 up to Rn. That's just a parallel combination of those resistors. So that circuit can be combined into a single current source with its associated parallel resistor. And then that's connected to the load. Now the IEQ, the equivalent output current, is simply going to be the sum of each one of those current sources. All of those current sources added together will give you the equivalent current. And the equivalent resistance is simply the parallel combination of all of those resistors. So R1 in parallel with R2, in parallel with R3, R4, all the way up to Rn. And we know that's equal to 1 over R1 plus 1 over R2 plus all the way up to adding up 1 over Rn. Now the conversion from this equivalent source to this equivalent source, that's just the source equivalency. So that VEQ will simply be IEQ times the equivalent REQ. And then this REQ is just the same as this one. So that one is just the 1 over R1 plus R1 over R2 plus all the way up to 1 over Rn. And if we were to write this out now, the equivalent current, I1 is V1 over R1, I2, V2 over R2. So let's put those values back in. V1 over R1 plus V2 over R2 plus all of the other current sources all the way up to N, Vn over Rn. That gives me the equivalent current. And now the equivalent resistance is this equation, is 1 over R1 plus 1 over R2. And I'm multiplying it, so I can just do a division there and just have on the denominator here 1 over R1 plus 1 over R2 plus all the resistances up to Rn. And that right there is Millman's theorem, the equation for Millman's theorem, which says that you can take a circuit with a set of parallel voltage sources and convert it into a single voltage source with its equivalent resistance. So this is a circuit analysis theorem that only applies in one's particular situation. It's not as useful as the other ones, which are a little bit more general and can be used in a number of different situations. Nevertheless, if you ever do come across this kind of situation, this might be a set of series batteries where there's slightly different voltage values. Easy to convert that into the equivalent voltage. So stay tuned for a video on the application of Millman's theorem. How do I wrap this one up? Do I just keep saying the same thing as I normally do? Why do I always do this on the fly? Why can't I just plan ahead and have something inspiring and creative to say at the very end? I guess I'll just say thanks for watching. See you next time. Bye.